let's go ahead and get going. Let me introduce you here, Xiaowen. So I'm thrilled to have Xiaowen present at our ECSS Symposium today. Xiaowen and I have worked together for some years. Xiaowen's been a member of, I think, both the TeraGrid and the Exceed extended support, Xiaowen, or maybe just in Exceed.
Both.
Both, yeah. I thought it was quite some time. Xiaowen is the director of NCSA's new Cyber GIS Center for Advanced Digital and Spatial Studies, and is really a leader in the field of bringing kind of high-performance computing to GIS. Many years experience in geography and coming at this from a very solid GIS perspective, but really with the knowledge of high-performance cyber infrastructure as well. This is becoming more and more of a key area for Exceed, I think, and I was thrilled that Xiaowen could fit us into his schedule to give us a presentation today. So with that, please take it away, Xiaowen.
Thanks very much, Nancy. It's been a tremendous pleasure working with you for a number of years, and Happy New Year to the folks on the ECSS team. I suppose this is the first one, the symposium for 2014.
Yes, it is. You're starting things off right.
Yeah, it's thanks for the opportunity speaking with you the first time in 2014. As you saw the first slide, pushing the integration envelope of cyber infrastructure to realize the cyber GIS vision. So I'm trying to address this integration perspective in my talk. And Nancy asked me to talk a little bit about the general big picture of what I do. And as you see from the left of this slide, last year I was part of this committee putting together this report, Spatial Computing to 2020, addressing the active development in the field and looking to the future. And although GIS, Geographic Information Systems, are relatively old technologies, given the pace of technologies we're talking about here, high-performance computing in general. GIS is relatively old, but the new development is quite exciting and is dramatic. And you see the left side of the slide, bottom part, comparing what happened in the last century and the new reality, and I'm supposing each of you could make maps easily and go to Google Maps, for instance, and everybody today is using location-based services to find where to go and what cool things to do. And every technology platform, information technology platform, has a location component, including your iPhone and smartphones. So all these new developments have very significant implications. On the right hand, this is what Google paid a neutral firm to do last year. Google in general is calling this as geoservices. And the estimate is it's hard to see the small numbers. Let me read out for you. The geoservices accounting for about 150 to 270 $1 billion global revenue, annual global revenue, and this is in contrast to about $600 billion global annual revenue in airline industry. And a lot of us are playing video games. The video games is actually only $25 billion global revenue annually. So you see how significant this is and how significant in terms of scientific impact on people's lives, and how the synergy between science and technology are combined in this active field. And I guess this is setting up the stage, talking about a general area of our work in terms of cyber GIS. And in terms of benefits, as I was alluded to, the geoservices, Google's addressing in big way. USGS, which is a science agency in the U.S. here, they started this 3DAP program, three-dimensional elevation program, for producing the next generation elevation data sets for the nation that would be broadly useful in sciences such as hydrology, geosciences broadly speaking. And this is going to generate between 2 and 9 petabytes raw cloud LiDAR data. This is just raw data. And there are multiple new type of data sets based on this raw data that could lead to multiple times of raw data volumes. So the implication here is this big data leads to tremendous value to science and to the society, but at the same time posing dramatic challenges to computing. So the notion of integrated studies here centered around computing and data. Of course, geospatial domains are long time studied, including fields such as agriculture, environmental sciences, and even business. So a lot of fields are dealing with geospatial data. There's a whole lot of richness, not just volume, and the complexity of data involved, and we're collecting all the time. And this, of course, involves privacy issues when you are considering the locations of people as far as their health is concerned, as an example. So it's a lot of things are going on in terms of the ability of integrating data and computing, and a lot of methods in different domains employed. So we're talking about multidisciplinary research in this general context. If we refer back to the notion Dan Atkins, who led the draft of the Blue Ribbon Report of cyber infrastructure in 2002 or 3, the notion he used is this borrowing rings that speaks to the spirit of cyber infrastructure in terms of integrating a number of high-end components from the computational space together, arguing that you have to get all the pieces together to deliver the promise that is the whole more than the sum of its parts. And this is very much true in the general picture of cyber GIS. As I argued, if you play with Google Earth or Map, you see the data visualized, but you also understand behind the scene a lot of dirty work's done in the computing space. The GIS integration clearly reflects the spirit of cyber infrastructure because it engages integrated workflow. Whenever you see maps, you want an immediate response to your perception. And this is quite unique comparing to some conventional sciences in the HPC domain. If I do a simulation, it's perfectly fine for me to move my data out of high-performance computers to do post-processing and to do scientific visualization. But in GIS, we have high demand for immediate user response because I want to see the maps whenever I want to pull some data up. And I think Google, as an example, has spoiled the users of these digital maps because we could easily get to massive information just on our fingertips. So how do we deliver the promise of integration of cyber infrastructure to bring access to massive, diverse geospatial data, and also on top of that, analytics for immediate response to users' requests? In contrast to the conventional HPC science domains, you just have to load up massive data out of the high-performance computers to post-processing. So I see this is a major opportunity and challenge coming from the cyber GIS side because you need to include high-performance computing and at the same time working with the big data and at the same time leading to high-fidelity visualization and at the same time maps are looked at by oftentimes number of users simultaneously, typical examples for decision-making applications. So look at cyber GIS, this picture, you see the peripherals that includes all the core elements of cyber infrastructure that requires integration to make this work. And how to achieve this? It's not a trivial task. because this involves layers and tiers of new knowledge we have to produce and new capabilities not necessarily readily available from the conventional HPC-based cyber infrastructure. And we're really talking about an ecosystem driven by many applied domains, as I mentioned earlier, from agriculture to business to health to emergency management, geosciences, social sciences, humanities, you name it. And this have to be enabled by the advances of digital technologies, cyber infrastructure in particular. And in the middle, we see, for instance, Google is pulling up a big ecosystem from Google, computing engine to Earth engine and lots of apps and services. And from scientific perspective, we see a parallel for the need of such an ecosystem. And I think CyberGIS is filling this gap for scientific research purposes. So what are grand challenges and opportunities we see from advanced cyber infrastructure perspective? And we need to create, this is not something already existing, to bring advanced cyber infrastructure and the geospatial technologies together. And this is, of course, not only about innovating infrastructure and systems, but also about advancing geospatial research and education in major ways. And the opportunities are huge and rewards are potentially also huge, but the challenges are also dramatic here. Data, as I mentioned, is a big challenge because when we deal with geospatial data, it's not about volume, and it's not about velocity, and it's not about variety. As I mentioned, there's privacy concern, and it's shared access, and it's coming from different domains. Oftentimes, we have to integrate. As we know, different domains have different ontologies, leading to many, many different formats of data. And then there's a different integration, geographic units we need to worry. And simply, for those of you who might not be familiar with GIS, for three-dimensional Earth projecting to two-dimension, there's this hard problem. You cannot simultaneously preserve area and shape. This is a math problem, essentially. And in order to get around this problem, there are hundreds of projection schemes developed. But the problem with Google Earth or Map or Microsoft Bing Maps, they are using only one kind of projection, which is what is called a web makeator. So this causes a lot of problems when you integrate the data together. Excuse me. And particularly when you need to work with different data formats and the different ontologies of different geospatial domains. And when you work with massive data and trying to bring them together with different projection schemes, even transforming the data across different projection systems is not a trivial task. And in the collaboration Nancy mentioned, we're working together. We partner with USGS to come up with scalable mechanisms to transform different projection data, geospatial data, into a common framework for data integration and further analysis. So this is an example, as you see from the slide, is showing the USGS national elevation data set that is 1/3 arc, 10-meter resolution. And what I mentioned earlier, the new USGS 3DAP program is leading to a 1-meter resolution national elevation data sets for much improved representation of terrain, building structures across the nation, for a lot of new sciences in the geosciences domain and in infrastructure, environmental studies. So another example in terms of collaboration that ECSS is benefiting essentially is this group. This project we've been pursuing together, led by David Tarboton from Utah State. This is a I would say a typical CyberGIS workflow, a software tool developed by David Group working on digital elevation data, which is a derived form of the elevation data I was talking about from USGS, their program. And as you see here, one input data, the terrain data example, could lead to many intermediate results. And this is a workflow we are experimenting with using Trestle at SDSC. So one input sample with a few gigabytes could lead to 10 times intermediate results and then the final results. So if you play with 1 gigabyte, your results will lead to at least 10 gigabytes to interpret. And we're talking about tens of gigabytes as a typical user file, and you get to hundreds of gigabytes output to interpret and visualize and to and also link to hydrological models and other models to be taken as input. If I have time, I'll show you some live demo for this kind of workflow, and the boxes are so small and it's not meant to serve as vision test for you. But I'm getting to the point here is for this analysis, getting to the integration aspect. This is about computing. A lot of steps is computing, and also about visualization and data access. So right now, we are running this workflow, part of this workflow on Trestles, getting the calculations done, but we have to move the data to the CyberGIS gateway, which is an online environment for users to start this workflow. So the computing for multiple tens of gigabytes took about half to 1 hour, but the data manipulation processing after the calculation could easily take another hour, and the visualization take another half hour. Move the data to the gateway takes another half hour. So for a typical user scenario, you would have easily 2 to 3 hours gone. So the current cyber infrastructure, although solving the scalable needs for dealing with larger data sets, but clearly not meeting the requirements we have from CyberGIS perspective. Because the typical use case of this is whenever I get to this data, I want to immediately see and explore the results as the computing is taking place. But now I will show you in the live demo, for a user analysis, I have to wait for a couple of hours to get to the maps I want to see immediately. And this requires highly integrated cyber infrastructure environment. And currently, I think Exceed is not there yet. So we need this integration aspect to be pushed very hard to deliver the promise of CyberGIS workflow as exemplified by this TAO-DIM case.
Xiaowen, we've had a couple of questions come in for you. One is whether the TAO-DIM workflow is Linux-based or does it involve a Windows platform?
This is all Linux-based.
Right, that's what I thought. And there was a second question about ArcGIS and Esri tools and whether any of them were available in an HPC environment through CyberGIS.
Good question. TAO-DIM does have ArcGIS plugin, so if you want to use TAO-DIM for smaller data sets, you could use ArcGIS to do the workflow as we're talking about here. Not as sophisticated as shown on this slide, but has some simple workflows. I will make another point, that is, because of the exposure of cyber infrastructure, we're able to get to bigger data sets and also tying the computing resources and the visualization together. This allows the TAO-DIM PI, Dave Tarboton, to actually pursue more sophisticated workflows than he would be able to do in the ArcGIS desktop version. The question about whether ArcGIS, the mainstream GIS software, has HPC support, unfortunately, answer is no. And they are primarily dominating the market from the desktop GIS perspective. They are interested to scale a lot of methods and algorithms up, but that's not really the in-house expertise they have for at least the recent history. They've been dealing with this problem. But they recognize the importance, and I have a later slide show the collaboration we have with Esri. This is actually coming from an online article Esri published. And you saw Esri ArcGIS also developing an online environment which shared a similar vision as we do with the CyberGIS Gateway, but they are largely linking up to their existing products and services as shown on the slide on the left side, and they see potentially they would be integrating with us, the scientific community, through open APIs and the services. So they see what we do is complementary to what they do, and I do not see they have actively put up new products in the support of HPC necessarily, but they clearly see the benefits through integration with the scientific work and the CyberGIS Gateway we've been developing.
Xiaowen, would you mind taking just a minute or so to entertain a question from TAC? It might be better than me serving as the intermediary. There was a question about limitations on the file size or the number of files that can be ingested by ArcGIS at any one time.
Okay.
I might let TAC folks, can someone ask Xiaowen directly what you'd like to know? Might be more efficient.
Hello, Xiaowen. The question is related to the limitations of the ArcGIS platform that we generally are aware of. I'm not sure if this concern got fixed in the recent most versions, but from what I heard, there's a 2 GB limit on the file sizes that can be ingested by ArcGIS for displays. Is that right?
Yeah, and I think this is perhaps recently tied to their licenses. I assuming you are talking about ArcGIS Online.
Right.
Yeah. So they have limit on the user uploaded data size. I think the evolving piece, initially when they released it's only 100 megabytes or something, and then I think they bumped up to 2 gig sometime late last year. I think this will continue to go up. But in terms of the data to be analyzed, when you put that data into ArcGIS Online, that is quite limited. ArcGIS Online does not promise to be able to analyze the data you upload there. I think the function feature they've made available on the uploading data side is primarily to federate data sharing. So what we do in the CyberGIS research has a major focus on analytics and the scalability of analytics. The example I used for how DIM workflow there is to be able to scale the analytics up to large data sizes and potentially different kinds of data integrated for analytics, which represents the most cutting-edge research. I think the industry is at the moment looking to academia to figure out smart solutions, because this, as we could imagine, the integration of HPC and the big data platform expertise with the understanding of what analytics do.
Thank you.
Thanks, Xiaowen. Sorry for the interruption there. But
No, feel free to infuse questions into my presentation. I think more interactive here means more effective sharing of experiences. So that's actually quite good.
Terrific. Thanks very much.
So another example is, as we know, simulations are the kind of regular work we do in the HPC world. No exception here for the CyberGIS world. But the difference in the CyberGIS world dealing with geospatial simulations is we hope to get the geospatial simulations work in an interactive mode. What that means is, as we know, geospatial simulations a lot of times are dealing with some emergency situations, such as for evacuation purpose or for understanding how disease is spreading. This is very different from understanding how the universe is evolving. To understand how the universe is evolving, we could run big simulations, run Monte Carlo validation, summary of many ensembles, and do scientific visualization producing movies. But in geospatial simulations, we are eager to get to what this simulation telling us as we are running the simulations. So that time pressure ingested by the use cases of CyberGIS is phenomenal. And I think that is pushing, again, the integration nature of cyber infrastructure, because this has to pull the high-performance computers together with visualization engine, together with data access, data engine, and capabilities. And this has to happen very quickly for the nature of applications we're talking about. So this example is simulating millions of agents moving around, spreading diseases. Again, can you make this kind of simulation as part of CyberGIS, presenting desirable user responses? And this gets us to another stream of major CyberGIS applications are normally for spatial decision making. So how do you allocate facilities, such as a new Walmart store, or in this case, we did study on where to locate biofuel facilities for refinery or for biomass storage. And as we know, this is a new kind of energy source. The existing energy infrastructure is not yet be able to accommodate this kind of new infrastructure needs. And where you would want to put your facilities, considering the usage of water, environmental impact, and most importantly, of course, for any emerging economy, is the cost-benefit balance. And this is, again, involving, as you can imagine, a number of stakeholders, not only the folks involved in the production of energy, but also the people who get impacted, such as farmers need to provide the biomass to the facilities, and the people living in the area concerning about the environmental impact. And the system like this, again, presenting and sharing this information together with many what-if scenarios analyzed based on simulation models as to where to place these facilities. Again, you would need to drive very hard the integration of computing, data, collaboration, and visualization all together. If you don't have all of those pieces together, this would not be serving as a useful decision support tool. And about collaboration, as we know, team sciences are now becoming very typical, and this is relatively slowly happening in the geospatial world, because especially social sciences are not so much versed into the collaborative team science context. We've been pushing hard in this space, trying to understand what the collaboration could bring benefits to social scientists. This example is a utility, what we call spatial regression. As we know, regression is a very popular statistical trick. used in many, many science domains. And in social sciences, particularly econometrics, people are using spatial regression methods, which actually needs multiple experts tune parameters and improve the model altogether. And this utility we set up in the CyberJS gateway allows multiple users to work on the same model simultaneously, which would otherwise not possible if you're just using desktop GIS tools or any other standalone tools. So this shows the benefit of collaborative work in the context of CyberGIS, but also engaging social scientists to be versed into collaborative work. As Nancy mentioned, we've been working together largely for the collaboration in this project, that is to research the next generation CyberGIS software and tools. This is a project spanning 9 institutions and collaborating with Esri, the producer of ArcGIS tools, and also USGS. I mentioned earlier they present to us huge data and analytics problems in the geospatial domain, but it has tremendous scientific and societal benefits from what they do. And part of the aspiration here in this project is to deal with complex and evolving cyber environments. As we know, GIS largely representing technologies so successful in the single-core desktop world. Now we see the mobile world, we see the parallel world, many-core, multi-core world, and we see tremendous need to come up with a new generation of basic set of GIS spatial algorithms that are able to take advantage of the new world that is so parallel from the hardware to the software side. And
Xiaowen, I'm going to mute the background noise just for a moment, okay?
Yeah.
Presentation mode is now enabled.
Okay, there you go. Please continue. Thanks.
Yeah. So very quickly go through the major transformation in cyber environment, but a very new world to the GIS crowd. And this, from cloud service-oriented to very parallel world, as we all familiar with, and of course heterogeneous architecture, including accelerators, GPU, and location-based services for mobile devices. And what this means is we, again, have to think of an ecosystem that needs to be integrated in terms of the individual components and the services coming together almost at will for many, many applications in the geospatial world. And this is, as far as integration is concerned, extreme scale, right? Computing, data information, and communication. And this is non-trivial because we're, again, talking about typical CyberGIS workflow. Whenever you're talking about these digital maps, you want to interact with what you see. And whenever you want to interact with what you see, this poses huge pressure for integration from the under the hood and behind the scenes. As we know, high-performance computers, big data systems and platforms, and the visualization resources a lot of times provisioned as a cloud. Again, I argue that this is quite unique, given a little bit of experience I got exposed to the other sciences coming from the conventional HPC world. This kind of uniqueness in terms of the interactive user responses and also the diversity of applications requiring this kind of interactive user responses are very exciting to me, and I think is pushing the envelope of integration from cyber infrastructure perspective. And you could be talking about blue waters, and this is a very exciting toy, as we all know. Many cores and large memory, petabytes storage. But one of the projects we are currently working on is to understand how political redistricting is working and what are the options in that context are not necessarily available to not only politicians but also general public. To understand the optimality of political redistricting, we could use Blue Waters to get many scenarios. But the nightmare only starts when you have to sift through all these scenarios and making these scenarios available to the potential users who want to understand what all these options mean. And each run of optimization code produces tens of gigabytes data. And how do you put all this data on the map? And the workflow to get out of Blue Waters to make this available as interactive maps, as potentially part of a decision support tool, that process so far is too long. And I think we have to come up with very innovative strategies to pulling the necessary cyber resources together to enable this kind of interactive workflow I was referring to many times. So in the CyberGIS world, we see the kind of spectrum of potential users and use cases. There are Blue Water use cases I was mentioning. You run simulation or optimization codes, sometimes statistical analysis. And we have perhaps not a big community of scientists, users who are comfortable to get into HPC. Not a large community, it's still growing. And at the same time, we have a huge population of GIS users from different fields, as I mentioned earlier. And these users are even not comfortable with the complexity of tools like ArcGIS. And the users are growing in the population and in the diversity of the fields we're talking about. So we're seeing the need for lowering the entry door to perform analytics. And this is essentially the motivation for CyberGIS Gateway, to ease the experience of users not only to access GIS analytics in a straightforward way, but also access advanced cyber infrastructure behind the CyberGIS scene in a straightforward way. And between these two extremes, there's a middle tier. You would see there are application developers and want access to services, libraries, and this is sort of the middle where spectrum, and this is again going to broad applications and potentially lots of developers. I mentioned the richness of the communities involved, both the science and technology communities and also user communities of GIS. Now we broadly argue they become users of CyberGIS, because if you talk about GIS today, you're largely talking about CyberGIS, because the world is so connected in both the cyber resources and the problems we have to solve in many multidisciplinary ways. I already talked about this slide. Again, this is an example of an ecosystem we are talking about. Just like you are, using your smartphones, that is alone an ecosystem, because there's platform, there's applications, there are services, and a whole lot of people involved in different tiers of all the levels for making that ecosystem work. And we see CyberGIS clearly is moving toward, or has become, an ecosystem, and we see the mainstream industry is taking care of their business, and they are creating their own ecosystem, and they are interfacing to us, the scientific communities and the technology research communities, to exploit the strength we have, from high-end computing to advanced cyber infrastructure, including not just the computing, but also data visualization and collaborative capabilities. I mentioned the CyberGIS toolkit. This is a key deliverable of the CyberGIS project I introduced to you a few slides earlier. The P-Raster Blaster is collaboration. It's hard to see, but it's one of the blue text lines below the CyberGS toolkit heading there. That is for the map reprojection problem I was talking about. You got hundreds of projections. How do you make sure they're actually fitting to the same framework for data integration and also further analytics? And this is an open source repository. The idea is we want to grow the community of data scientists, computational scientists are versed into the geospatial domain. They need to understand how to parallelize and scale different CyberGS analytics and utilities to high-end computational systems. And we make this open source to help grow the community extensively. And the gateway part, as I was talking about, is largely to invite a large number of CyberGS users into the cyber infrastructure world, and this is ranging, again, for the CyberGS infrastructure from the example of Blue Waters to Exceed. We've benefited enormously working with the Exceed in the CyberGS research and also Open Science Grid, and of course, cloud is a major now infrastructure for CyberGS services. But if you're talking about CyberGS as a whole, all of these basic infrastructure pieces are coming to the horizon because of the richness of the CyberGS use cases, from data-driven to computing-driven to the needs of lowering the entry door for serving the responsive users' needs, and all of this demanding the integration we're talking about and a deep stack from the management of infrastructure access to supporting the broad spectrum of applications and sciences. So intellectually, from research side, we're talking about this integration with respect to the spatial aspect and also the computational aspect. Of course, this is linked to the extreme scale notion I was alluded to earlier about cyber environments. The idea here is how do you naturally infuse these two different, very different contexts together for solving challenging scientific problems and also solving challenging computational problems. And this is not trivial because my argument is we're not producing enough people and we're actually falling behind in our education efforts to be able to train the new generation that is able to cut across the spatial and the computational realms. And we need these people, the new generation, to be able to create new technologies and tackling challenging science problems that requires new technologies to be supporting the multidisciplinary and cross-disciplinary collaboration. And in fact, as part of the CyberGS software project and also several other activities, we're promoting the efforts in education and creating new curriculum, and in fact also foster partnerships to make this work because the demand is so huge for competent workforce. So how do we do this at Illinois? So last year the campus decided to launch a new center, and the center really is a multidisciplinary framework contributed by units from College of Liberal Arts and Sciences to engineering to agriculture and to library and information sciences. The idea is we would integrate research and education, have advanced user support also for the campus and beyond, and affiliated faculty from a wide variety of domains provide this framework for them to collaborate and educate the next generation. The vision is centered on integration and pushed up by the advance of digital technologies and driven by the opportunities coming from discovery and innovation across so many different domains related to geospatial. And this is largely for elements integration from CyberGIS and the synergy with advanced cyber infrastructure to many computing and data intensive sciences and applications. And this is, again, contextualized into geospatial sciences technologies pushing the development of CyberGIS. That is the last slide, and this is to acknowledge a number of funding sources and also partnership with the industry, helping us achieve what we think is exciting to do and give us a lot of fun. And the units I mentioned supporting the CyberGIS Center at Illinois. And thank you for your attention, and happy to take any questions or comments. And at the same time, I'll see if I could make some demos work.
Xiaowen, that sounds great. Let me unmute the phone lines. I've seen a question from TAC come in, and there may be some others as well. Just a moment.
Presentation mode is now disabled.
Okay, great. TAC, do you want to go ahead and pose your question?
Thank you, Nancy. Xiaowen, on one of the slides you had mentioned data provenance. It was early on, maybe slide 4 or 5.
Uh-huh.
So what work are you doing towards that end?
So that was a slide I think I was talking about CyberGIS vision, and that is one of the key capabilities or research topics centered on workflow and provenance. One example in that research is to analyze the provenance traces when you would link up a set of analytical services for spatial decision making. More concretely, we are using a spatial econometrics toolkit. It's called PyCell, which is an open source Python-based scientific code. There you would analyze point-based or polygon-based spatial data, but most importantly, you derive indicators of spatial dependence, such as in the housing market or others, or crime analysis. So when you work with such kind of data, you could easily imagine you would have observation data, but also you work with the population data from census. And you would estimate what we call spatial weights, which is a metric for determining the spatial dependence structure. And you could easily get lost when you're pulling multiple data sources and you're generating spatial weights and you specify parameters and you run your analysis and you get to results on the map. The idea is how could you keep track of what is happening along the steps involved, and what are the ontologies and what are the standards we might need to define to make this a collaborative process from the data input to the specification of the models, to the specification of the parameters, and also to the presentation of the results. So that's an example posing some interesting challenges for formulating provenance and also for keeping track of provenance and also for presenting the provenance.
So when your data goes for long-term storage, do you also plan to send the provenance information with that?
Yeah, so the design, currently the example I showed in my slide with respect to the collaborative geospatial knowledge discovery using the spatial regression model, you could see that as a simpler example of provenance needs. I was talking about the idea is now because you could work on a single model among multiple users, and that model instance would be recorded in terms of the parameter values coming from different users and also the model specifications. And these are, you could call as provenance with respect to analysis workflow. and this information is stored not closely, you could say it's stored in a coupled way with a analytical workflow as opposed to data. But clearly, the analytical workflow is also linked to the data as a part of the representation of the workflow. Did that answer your question?
I'll follow up maybe later. Maybe other people also have questions. If there are no other questions, maybe I'll ask one more question. Else, I'll leave the time for other people to ask you questions.
Chauvin?
Yes.
This is Sudhakar here from NCSA. Yes, so this is kind of related to what you have been talking about, this provenance and archiving and so on and so forth. So you mentioned that the time it takes for some of these, big workflows is kind of not conducive for, providing this data which the people expect to be kind of ready, on their fingertips. Is there a model where you can actually, pre-run these simulations and archive them, and then if you find the parameters that the user is seeking, can quickly go and, retrieve the result from, an annotated archive and provide that essentially instantaneously or with very short time lag?
You could do that, and that's probably a standard practice happening as the state of the art. But the vision we're addressing here is that is not adequate, because as you could imagine, we are instrumenting Earth and the human environment and on an unprecedented pace. Satellites is orbiting and GPS is collecting data. So the notion is that when you run simulations, you could actually get to up-to-date observations. So the traditional scientific simulation conventions say, oh, I'm using some data to stage my simulation and get some predictions. I'll be happy with that until I publish that paper. But in the geospatial world, we increasingly see that you are continuously getting to up-to-date observations that are valuable to be ingested into your simulation or analytical workflow. So we need an open framework and a capable, scalable infrastructure to accommodate this on-demand needs that are originally posed by interactive user requests, but by nature, it's actually enabled by on-time observations we see in this geospatial world.
But if the simulation takes a long time, by the time you actually provide the result, the data is already changed, right? If the data is changing so rapidly.
So we need to shrink that gap. And also we need to continue to push up the computing power needed to shrink the simulation time, but also we need a adaptive framework to link the simulation to up-to-date data. Data simulation is a very important research topic to bring the up-to-date data world to scientific simulations. So if I may have a few minutes, I'll show you probably through a few examples as to what I meant by interactive user experiences, and also the examples I probably could show if we have time here for the broad scientific use cases of CyberGIS. So Nancy, is it okay if I start now?
Yep, that would be terrific, Xiaowen.
Okay, so I named a new analysis doing tau dim. This is still in the development stage, and as we all know, presenters are not encouraged to do a live demo. If I get this crash, don't take any negative impression away. But this is the tau dim workflow. As you see here, it's showing a simplified representation of the workflow steps involved for analyzing, you could say, just terrain data. This is the data representing topography of Earth. A few simple steps, and you have multiple stages of the workflow here. You might go ahead to select data, which doesn't I might be timed out. Let me log out again.
What is this excited about?
Sorry, what was the question? I'm not intending to show you my emails, but I have to do this. Okay, so I was logged out. As you can imagine, this is accessing backend computers, including Trestle. We actually doing serious work of protecting access. Also partner with, I think, cyber infrastructure effort directed by Vaughn Welch at Indiana. He's setting up this cybersecurity project, helping us to assess the security readiness for this online environment. So we took advantage of that partnership. Terabyte level. On the fingertip of any users of GIS want to analyze parts of this data. And in this particular case is for the tau dim, so the analyzing the streams or river networks, hydrologic features of the so you have this, you could say, this select data and you submit. So I clicked twice, the button, so they submitted Nancy Tau DEM twice. I did not intend to do that, but I happened to click twice because the response was slow. So as now you see, they are hammering those two computing tasks that analysis is submitted for computation. So if you are ArcGIS user, you worked on Tau dim or any other analysis involved digital elevation model data. And this is not the way how the normal GIS tools are working. Because as happening, these are the computations getting submitted to Trestle, I suppose. And the whole workflow is just getting started. So what this environment allows us to do is you could submit additional analysis, sending as many analysis you want to this environment. But we're still not able to shrink the span of the workflow to get this to be as interactive as we hope for the desirable user feedbacks. We hope to do exploratory analysis. So what is the desirable state? Let me show you another application. This is the production environment of the CyberGS. Wow, that's interesting. Okay, so maybe I could show you another one, similar one. So there's less sophisticated workflow centered on this viewshed analysis that could get us into a more interactive setting. Let me start a again, similar user interface. This is also working on digital elevation data, same data. And what this computes is visible regions from selected locations. A lot of times used in urban planning and even in military applications. And you don't want to do this kind of analysis using large data sets and ArcGIS because that's not going to be easily done for some computational limitations the mainstream GIS tools have. And if I, again, so this would be a little bit more interactive because the computing is taking place not at SDSC, it's at NCSA, so we don't need to have a whole lot of network transfer. Perhaps within a few minutes, this workflow will be done. Again, if you work on GIS tools, regular tools, desktop tools on this kind of analysis, either viewshed or TAO-DIM, these are meant to be interactive exploratory analysis. So users are expecting to see results as they move through parameters and the selection of locations. But because of the computing challenges and the integration support among different cyber resources and elements, we're not able to do this in a fully interactive fashion. But the CyberGIS posing the requirements for the faster network connections and for faster turnaround time, for non-conventional management of HPC systems. If we're using queues, we know a lot of times we're not able to get through the queues without prior reservation for the computing to be done quickly. So as you saw here, it says analysis is queued. So this is using the conventional HPC resource access mode. I did not reserve anything for today's demo. And you probably get to my point is if we want to engage interactive exploratory analysis and again, based on the maps or sharing the maps, we see tremendous needs posed against the integrative aspect of cyber infrastructure. And I see also this could be perhaps adequately served if we have a centrally integrated facility with balanced computing visualization and data capabilities integrated together. Because if we continue to use the exceed mode, as a distributed environment, the majority of CyberGIS use cases would have to be working in a way without interactivity, without desirable interactivity, as we're talking about. So you see there are different status updated now. Analysis is actually running. This is, again, a resource local here at NCSA. And also you see the analysis as submitted on behalf of Nancy is also running. There are two globes are rotating. That's pushing mode from the resource to this environment, showing the status of this workflow. I could, for instance, show you a done analysis. This is analysis conducted earlier. That's essentially showing the results. The blue color regions are the visible regions from the locations of these red triangles. This essentially is what that ViewShed analytics does, and you could do this in most of the popular GIS packages, either open source or commercial. But we're running into the challenges of dealing with the larger size data, and also if you want to share this analysis across multiple users, you probably would go nowhere. So CyberGIS is addressing this need, but we're still challenged by the inadequate integration power of cyber infrastructure to enable this to the level we hope to get. Time, the 10 minutes after 1.
Yeah, I think I'm going to have to conclude the web conference, Xiaowen, but thank you very much for staying the extra time and for all our attendees as well. The nice thing is that these are recorded so they can be viewable at a later time by other folks, and if you send me your slides, we'll get those up on the symposium website as well.
I will send you slides later today.
Very good.
I'll let you control the time for any remaining questions, but I'm here. Could stay for extra time if needed.
Yeah, I think I'll need to shut things down at this end now, but if folks do have questions for Xiaowen, his contact info is also on the symposium website. So if you just go to exceed.org and search for symposium, or Google and search for ECSS-Symposium, you'll find the schedule with the abstracts and a link to Xiaowen's contact information and all the rest. So thank you very much for taking the time to prepare such a detailed and thoughtful talk for us today. Really appreciate it. Twice the amount of time people are usually on the hook for these talks, but it's a very big topic, and there are a lot of moving parts, so it was very helpful to have the extra time, I think, plus the demo.
Thank you, Nancy, for having me and organizing this.
Yep, thanks.